Good morning one and all. Today we will going to discuss about star to delta transformation and delta to star transformation in the network analysis. First we have understand about that the one port network and two port network. What is the one port network and the two port network? There are certain configurations that cannot be simplified by serial to parallel combination alone, and simple transformation based on the mathematical technique is readily simplifies the electrical circuit configuration, and that configuration is shown here. Basically this is the one port network. This is called as the one port network because of that there are only one input, and here is only one voltage we have able to apply across it, and only there is one current is flowing into the device only. That's why it is called as the one port network. Then next, when any voltage source is connected across the terminal and the current entering through the any one of the terminal is equal to the current leaving the other terminal. For example, the resistance, inductance and capacitance is act as the one port network. And other hand, the two port network is the circuit having the two pair of the terminal, and each pair behaves as the one port current entering in the one terminal, and that must be equal to the current leaving the other terminal. In this figure we have understand about that the two port network. In the two port network, one here is the one is the input port and another is the output port. We are able to apply the voltage drop across the terminal A and C, and current is entering into the junction. From the other side, current is leaving from the junction, and here is the output port, which is called as the output port, and voltage V2 is applied across the terminal. This is called as the two port network, and one for the input port and another for the output port. On the other hand, the two port is the circuit having the two pairs of the terminal, and each pair behaves as the one port, and current entering in the one terminal must be equal to the current leaving the other terminal, which is called as the two port network. Then the most important subclass of the two port network is the one in which the reference terminal and which is called as the one is for the input port and another is for the output port, which is called as the two port network. So from the figure 6.1c, here is to show the pi network, because it is the look like the pi symbol, and it is connected between the input port and output port is also available, because this is the two port network. The resistance R of AB is connected between the terminal A and B. The resistance R of CA is connected between the A and C, and connect R of BC, this resistance is connected between the terminal B and C. So it is required to convert into the equivalent Y network, or it is called as the T network also. So in between the terminal 1 and A and O, the RA is connected. In between the terminal O and B, the RB is connected, and in between the terminal 0 or O to the C, it is called as the RC. So it is the interconversion. So in the delta to Y conversion, we have able to obtain in there in between the terminal A to the C, A to the B and B to the C, R of CA, R of BC and R of AB that will be connected. So R of C, it is the interconversion between the R of CA. R of B, it is the interconversion between the R of BC, and R of A, it is the interconversion between the R of AB. So it is converted into again Y network to the delta network. So this configuration may often be handled by the use of delta to Y transformation, and one of the most basic three terminal network equivalent is that is the three resistance connected in the delta and Y connection. So these three terminal network can be redrawn as the four terminal network, and which is a very useful expression for the direct transformation between the delta to Y transformation. So conversion between the delta to star. So next part we have seen here, let us consider the network as shown in 6.1e. Assume that the resistance R of AB R of BC and R of CA in the delta network. So our problem is to be find the value of R of A, R of B and R of C in the Y network, and that will be producing the same resistance when measured between the similar pairs of the terminal. So we can write in the equivalent resistance between the any two terminal in the following form. So here let us consider the network shown in figure 6.1e, means from this figure 6.1e. The resistance is connected between the A to the C, A to the B and B to the C. So we have convert from here R of A. So in R of A, what we do in between the terminal A and C, means here between the terminal A and C, here A and C, there is R of A plus R of C. Okay, means R of A plus R of C in this way, R of A plus R of C into R of CA. R of CA means this resistance is in parallel with series combination of this resistance, means R of A plus R of C, which is equal to R of CA into R of A into R of B, means these two resistance are parallel. So RA plus RB upon RA plus RB plus RC. In this way we have to be right now this equation R of A plus R of C, which is equal to R of CA inside the bracket R of AB plus R of BC upon R of AB plus R of BC plus R of CA. Then in between the terminal C and B, in between the terminal C and B, again we move in backward, in between the terminal A and C and B. Here the terminal in between the C and B, there again R of B plus R of C. So in between the terminal B and C, here again these two resistance are connected in parallel, R of AB and R of C in parallel with this resistance. In this way we move R of C plus R of B, R of AB and this R of AB plus R of CA, these are two resistance are connected in a series fashion. This R of AB plus R of CA, this will be connected in a series fashion. Then R of BA, then its equivalent resistance is R of AB plus R of BC plus R of CA. Then between the terminal B and A, again R of B plus R of A, which is equal to R of AB inside the bracket R of CA plus R of BC upon R of AB plus R of BC plus R of CA. Then combining the above three equations, then we can write now the expression for R of A plus R of B plus R of C. We have to be moved towards in this way, R of A plus R of C, R of C plus R of B and R of B plus R of CA. In this way we have right now that equations. Then again there are 2RA, 2RB, 2RC. Again these two gets cancelled. Here is again common the 2 from RHS side and 2 for LHS side, both are cancelled, and to form the new equation RA plus RB plus RC, which is equal to RAB RBC plus RBC RCA plus RCA RAB upon RAB plus RBC plus RCA. Then subtracting the equation 6.1, 6.2 and 6.3 from 6.4, means from that equation 6.4, from that equation we have substitute 6.1, 6.2 and 6.3. Then we getting the result here R of A. R of A is R of AB, R of CA upon R of AB plus R of BC plus R of CA, is A to B, B to C, C to A, and R of A, R of AB, R of AC. Then R of B is R of AB, R of AB, R of BC upon R of AB plus R of BC plus R of CA. Means whatever here A resistance, that is AB, AC. Then here B, BC, AB, and R of C, BC, CA upon R of AB plus R of BC plus R of CA. In this way we have find out from delta to star conversion. Then conversion from star to delta in opposite way. To convert the Y to delta relationship, there is R of AB, R of BC and R of CA. There must be obtaining the term in the Y resistance, and which is called as the star to the delta transformation. So we have calculated the first. We can write the current expression through the RA. There is a IA which is equal to VA minus VN upon the RA for the Y network. And for the applying the KCL for Y connected network, we assume that A, B, C terminal having the higher potential than the neutral. Then we have write the equation VA minus VN upon RA plus VB minus VN upon RB plus VC upon VN upon RC, which is equal to 0. Then combining this equation and to move from LHS to the RHS, the next equation is Vn into inside the bracket 1 upon RA plus 1 upon RB plus 1 upon RC, which is equal to VA upon RA plus VB upon RB plus VC upon RC, and Vn which is equal to, from that equation we have calculated the Vn, then move this parameter from the RHS side. Therefore Vn which is equal to VA upon RA plus VB upon RB plus VC upon RC upon this parameter 1 upon RA plus 1 upon RB plus 1 upon RC. Then for delta network, we have seen from the 6.1, the current entering at the terminal A, which is equal to current leaving from the terminal A. So we calculated the value of I of A. So I of A which is equal to V of AB upon R of AB plus VAC upon R of AC for delta network. So from equation 6.8, from that equation 6.8 and 6.10, 6.8 and 6.10, we compare these two equations. Here LHS are equal or same, LHS are same, hence here RHS is also same. Then we move towards, there is a VA minus VN upon RA which is equal to VAB upon RAB plus VAC upon RAC. Then using the Vn expression in the above, then we get there is a VA minus Vn. This expression for Vn is given. Expression for Vn. This Vn we have substituted here. Therefore VA minus this equation VA upon RA plus VB upon RB plus VC upon RC upon 1 upon RA plus 1 upon RB plus 1 upon RC upon RA, which is equal to this equation. There is a V of AB upon R of AB plus VAC upon RAC. Therefore this equation is written again in this way. There is a VA minus VB, VA minus VB upon RB plus VA minus VC upon RC upon this equation 1 upon RA minus 1 upon RB plus 1 upon RC upon RA. Therefore this equation we are multiplying such a way that this equation we calculated it. There is a VAB, here is a VAB upon RB plus VAC upon RC, means this is this potential difference we write now here, V of AB upon RB plus V upon AC, here V of AC upon RC upon 1 upon RA plus 1 upon RB plus 1 upon RC upon RA, which is equal to VAB upon RAB plus VAC upon RAC. This is the equation number 1. Then from that equation we have coefficient for voltage drop across the V of AB and V of AC we calculated. Then we move towards the to find out the resistance value by the interconversion 1 upon RAB, which is equal to 1 upon RA RB upon 1 RA plus 1 RB plus 1 RC. Therefore R of AB which is equal to again the reverse of this equation, and this is multiplied the inside the term, then RA gets cancelled, there only RB should be remains here. Here RB gets cancelled, only RA will be remains here, and this equation RA RB upon R of C. Therefore we calculated the value of R of AB Here is R of AB, which is equal to RA plus RB plus RB upon RC. Therefore, R of AC is again we calculated RA plus RC plus RC upon RB. Similarly, IB for both network are given by means IB and VB minus VN upon RB. The similar expression we have to be find out here, R of BC, which is equal to RC plus RC upon RA. Then we need to transform the delta network to an equivalent Y network. The useful expression we want to getting from 6.5 to 6.7, and that useful expression on other hand there is 6.12 to 6.14 we have used for the delta or Y to the delta conversion. Then summary of the star and delta transformation. Basically this is the delta which is represented by in between the port R of AB, R of BC and R of CA, that will be given, and we have converting from there R of AB, BC and CA, there is R of C, R of B and R of A. The equivalent star or Y resistance connected to the given terminal is given to the product of the two resistance are connected between the terminal and divided by the sum of the delta resistance. The equivalent delta resistance between the two terminal is the sum of the two star resistance connected to those terminal plus the product of the same two star resistance divided by the third star resistance, that will be shown in the 6.2. My dear students, all of you understand the star to delta transformation and delta to star transformation. I hope that you understand the concept between this transformation in the network theorem. If any doubts, any query regarding for this star and delta transformation, delta to star transformation, you write on my comment page. Please subscribe my channel and click on the bell icon. Thank you. Have a nice day.